Bismillahirrahmanirrahim. Assalamu alaikum. Welcome everybody. Um, this is a short lecture on linked objects. It's part of the data structures and algorithms course that I teach at Prince Sultan University. The main purpose for this lecture is to provide a forum for students to go and look at the video and review some of the key concepts used in this course. In this lecture, we have three main topics to be covered. Very briefly, I'm just going to show a single slide about the different data types defined in Java. Next, we're going to look at memory allocation, the very fundamental concepts that you have probably learned in the initial programming courses. Then we're going to talk about linked objects, what are these and how do you create them? And finally, how do you build a simple linked list using the linked object structures? So here we go, a very simple list of the different primitive data types defined in Java. Again, you have already studied these, but since I will be using integer data type here in these slides, so I just wanted to show you that in 32-bit or 64-bit architecture Java virtual machines or JVMs, the size of integer is 4 bytes, which is 32 bits. So as you can see the range, you can store a large number of up to 2 billion something in an integer data type. Of course, there are many other data types like byte, short, long, and so on, but primarily we're going to be concerned with integer. One thing else to remember is a typical reference in Java, again in 32-bit or 64-bit versions of JVM, the size would be 8 bytes. So again, I'll very quickly go over this a bit later. Moving on to our first topic, which is memory allocation. So, starting with the very simple primitive data type, integer. Let's say I would like to define integer x. Now what happens is in your system, you probably or most likely have an operating system. It could be Windows, Mac OS, or whatever. When you say integer x in Java, your program is essentially requesting the operating system to allocate a memory for integer variable x. Now, as we've seen in the previous slide, the size of integer is 4 bytes, 32 bits of 4 bytes. So what will happen is your operating system is going to provide your program with 4 bytes of memory. When you say x equals 10, as the system executes this line of code, is going to assign the value 10 to the memory available to your program. So 10 would be copied in that particular memory location, which is already on the stack of your program. Now, how does an array work? So let's very quickly look at this. So when you say integer box brackets y, we're saying that we would like to create an array y of type integer. But this particular line does not necessarily mean that you're going to get the memory as we have seen in the previous slide. Here we're simply saying, please create a reference called y of type integer. So this is going to create a reference. Now in my slides here, I'm going to refer to a reference using a circular object, as you can see on the screen. When I say y equals new integer within box brackets 2. So essentially I'm asking my system to allocate a memory of size integer, and we would like to have 2 of these within our array. Now what happens is the operating system is going to provide you with 2 integer values. So since one integer takes 4 bytes, 2 would be giving you 8 bytes. And as again you have studied this in initial programming course, the first position would be index position 0 and the second would be index position 1. So in an array, the reference work like a pointer to a memory location. The memory location was dynamically allocated at runtime. If you say y equals 5, that would not be allowed because y is a reference type and you cannot copy a value which is 5 on the reference. 5 needs to go in the memory location. If you say something like this, y of 0 equals 5, this means that you would like to copy 5 in location or index 0. So you can see copy 5 in there. If you say y of 1 equals 7, that would definitely copy 7 in index position 1. So if I would like to print something from this array, let's say I would like to print 5, I would have to say print y of 0. Again, very quick review. Here y is a reference to the memory location. We create the reference, but the memory would be provided from the system to your program. Moving on to object data types. Now for reference, I would like to go with the little bit of code written on the left side of the screen. So we have a very simple Java class, public class obj, which has only one field, which is integer value. We define the default constructor public obj, in which we're initializing the value val equals 0. Now let's see how do you define an object. So if I say obj z, that's going to create an object called z of type obj. Now does that mean that we have, is that a reference or is that a memory? Let's see. Z would be a reference and not a memory. So you would have to request memory from the operating system. To do that, we will say z equals new obj. So we're calling the default constructor. This is going to create is going to request memory of type obj and allocate that to your reference z. Now here we have to be a little bit careful. Because of the overhead of object-oriented programming, we need to have a header for each object that will be created likewise. So here, the header size is 16 bytes based on simple assumptions, and value, since it is an integer, so that's going to request 4 bytes. Altogether, the size of this object would be 16 plus 4 is 20 bytes. Now why is it 16 bytes? Again, it depends on the different versions of JDK that you're using. In any case, the minimum size would be 16 bytes. It could be a bit more. Another thing to remember is that Java development environments, they use padding, which means that the total size of the memory should be divisible by 8. If it is any less than that, it's going to include some extra spaces to make it divisible by 8. Now, if I say z.val equals 5, that will copy 5 in the field val, which is defined within the object referred to by z. Okay, let's look at another simple example. Here I'm extending the class by writing another overloaded constructor function. So public obj, which is taking a single parameter integer x. We're simply initiating the value of val to this new parameter value x. So in the middle of the screen, the code that we're looking at is still the same code that we've seen in the previous example. Let's create a new object. So here we're saying obj_z2 equals new obj parameter 7. Now this is going to call the overloaded constructor, which essentially means first we're going to create a new reference z2, which is going to point to a new memory location of type obj, and we're copying 7 in this object. Again, the size of this object would be 20 bytes, similar to the previous one. All right, here's another example, and we'll continue using the same example for the rest of the concepts in these slides. So let's first look at the code on the left side. We have public class car. A car has two fields, integer seats and double engine. We're defining two constructors here. So first constructor is a default constructor where seats equals 4 and engine equals 2.0. The overloaded constructor is taking two parameters, integer x and double a, and we're initializing the two fields based on these past values. Now let's see. When I say car Ford, Ford equals new car 7, 3.5. So what happens here is Ford would be a reference of type car, which is requesting new memory from the operating system. Here, again, we're going to have the header with size 16 bytes. We have seats, which is integer type, so that will be 4 bytes. And we have engine, which is double type, which would be 8 bytes. So altogether, the size of this object would be 16 plus 4 plus 8, which is 28 bytes. Okay, let's see if we can copy a new object. So we say car VW or Volkswagen equals new car 4, 15. That's going to create a new memory location that is going to copy values 4 as seats in the Volkswagen object and 1.5 as a value of the engine. Let's see how arrays work with objects. So here I'm creating an array called cars with a capital C, of type car. And the size of the allocation is 2. Now, what this is going to do is going to create a reference cars pointing to a memory location of this shape. So we have a header, which is 16 bytes. And we're going to have two index positions because you wanted two index positions. So we have index 0 and index 1. And each of the values or the objects is of 12 bytes. Again, why 12 bytes? Because 4 bytes is coming from the integer seats and 8 bytes is coming from the double engine. So here we have cars as an array of type object. Let's see if we can copy some values in there. So if I would like to copy seats 4 and engine 1.5 in the first position in the array cars, I would do something like this. Cars of 0.seats equals 4. Cars of 0.engine equals 1.5. So that will copy these values in the first index position, which is index 0. Next, let's copy some values in the other object, which is currently empty. So you're going to say cars of 1.seats is 7 and .engine equals 3.6. So there you go. We go and copy these values in the array. Here's a small exercise for you using the same code on the left side. If I define an array called Toyota and initialize it to size 5, what will be the size of the Toyota object in bytes? I'm going to pause here for a few seconds. Let's see if you can answer this. All right. So the solution is the header would be 16 bytes. And because each of the object is 12 bytes long, so since you have 5 objects, that will be 12 times 5. So altogether, that should take 76 bytes. Let's see. So revisiting very quickly, what we've done so far is that we've learned about how memory gets allocated to your program. We've seen some examples of simple arrays, and we have looked at an example of array of type objects. Now, there are certain problems when we're using arrays to store object data. The first problem is to define an array, you need to know the size of your data. Why? Because arrays follow the static memory allocation type, which means that you need to provide the size of the data, and the operating system will go and fetch that amount of memory for your program. Second problem is the fixed size. Once you have defined the array, the size is fixed. There's no way that you can change that size. The only option is probably you have to destroy the original array and create a new one of a larger size. But what if the previous array has data in it? So it will become even more complex, because now you would have to relocate data from the old array to the larger array and then destroy the previous array. Think of it like this. Imagine you have a bunch of containers that you would like to ship to another place. If you put all the containers on a ship has a limited capacity. If you'd like to add some more and the ship is already full, you definitely cannot add more. You'll probably have to go and get a bigger ship. The cost of putting everything or relocating all the containers from the smaller ship to the larger ship could be a number of days and man hours and of course lots of money involved in there. So what's the solution for this? The solution is looking at linked data or linked objects. Here's a simple example. If you look at the top ARR array, there's a reference which is pointing to an array of size 4. Linked objects which allow you to connect the objects as if they're connected in a chain. So you can get the first object which connects to the second object through a chain, the second object connects to the third object and fourth object and so on. So you can keep adding more and more objects to this chain, and it can keep growing forever and ever and ever. The cool thing about this is that we do not suffer from the shortcomings or restrictions of an array. You do not need to know the actual size of the data. This means that you can increase the size of your chain as you go. Now let's move on and look at a simple code. So here I'm using the same code that we've seen before. Public class car. Car has integer value as a field, but now I'm introducing a new field which is called car next. So next is a field of type car. So you can think of like a self-reference. Next is probably of the same type as the car itself. We have a default constructor which is public car, which is initializing the value to 0 and next to null. Now let's look at how do you define an object. So car Ford equals new car. Yeah, so Ford is a reference of type car, and we're requesting the operating system to provide us with a memory location of type car. And we're going to get something like this. So Ford is a reference pointing to a memory location. Of course, we saw this before. There's going to be a header, which is the overhead of an object, which is 16 bytes. It's going to create one simple memory location for us of type car, which is 12 bytes. Here, integer is 4 bytes and reference is 8 bytes. Again, I've mentioned this earlier. In Java 32 or 64-bit architectures, the size of references is 8 bytes. Let's see. If I would like to copy some values in there, I would have to say 4.val equals 4 and 4.next equals null. So there you go. Simply go and put 4 and null over here. 4 would be the value type and null is the reference type. Okay, let's create two objects and see how do you link them. Now, for the way of simplicity, I've removed the overhead and the headers and all the things. So here, simply, Ford is pointing to an object, a memory location, with for as value and null as next. So create another car VW, Volkswagen equals new car, and we're going to copy 2 and null in there. There you go. Now let's see how we can link them together. Very simple. We're going to say for.next equals VW. So notice over here we had for.value is 4 and for.next was nil. Now if I say for.next equals VW, we're saying please link this next to the VW object. Now notice over here, I've just hypothetically put a number over here. This should be the address of the memory. Should you like to print the value of next, it'll probably give you something similar to it. Of course, not exactly the same. There you go. We have linked Ford with VW. Now here's a little trivia for you. If I say Ford.next is basically pointing to VW. If I say Ford.next.value, we're saying Ford.next, which is this object, dot value would be 2. So Ford.next.value is 2. Okay, let's look at another one. Let's see if you can connect 3 objects. So we already have these 3 objects, Ford and VW. I've removed the link over here. But let's see if you can create one. Here's a third car, Fiat equals new car, Fiat.value is 1, Fiat.next is null. So currently, all 3 objects are independent, they're not linked together. Let's create the links. So first I'm going to say Ford.next equals VW. So that should create a link from Ford.next to the VW object. Let's do the same for VW.next connecting the Fiat object. So all I have to say is VW.next equals Fiat, and that connects this next, which is within the VW object, to the Fiat. I'm sure you can see or visualize the chain now. Okay, here's a little trivia for you. Ford.next.value, Ford.next.value is 2. Ford.next.next.value is 1. What if I would like to get this one by using the VW object? All I have to say is VW.next.value would be 1. Alright, a little exercise for you. Make 4 objects of type car and link them together. Since I'm not providing any values to be inserted, so you can assume anything you would like. Let's wait for 5 seconds. Okay, so there's your solution. We like to create 4 objects. So we go like car 4 equals new car VW, Fiat, and key is new car. So we have 4 references. Each of them have their own objects. Since I have not initialized anything, so the default values should be 0 and null. Now, let's create the first link. So we're going to say Ford.next equals VW. And then we're going to say VW.next is Fiat. Then we're going to say Fiat.next equals K. There you go. Moving to the last topic, linked lists. So a linked list is a data structure which connects the different objects together in a chain. Here, the major difference is a linked list uses only one reference to point to the entire structure. if you look at this little picture on the right side, you can see that there's a head reference which is pointing to a node which contains 4 as a value. This object points to another object which contains 3. That in turn points to the object containing 2, and so on. If you notice, the last object in this list or chain, dot next, would be null. That should point to nothing. So a linked list can be created using different objects. Car head equals new car, head.val equals 1, head.next is null. So again, we've seen this before. This is going to create an object storing 1 as value and null as next, which should be pointed to by a reference head. Okay, let's create another object and see if we can link them together. So here I'm going to say car temp equals new car, temp.val equals 2, temp.next equals head. So we simply use a temp reference to point to a memory location storing 2, and instead of temp.next equals null, here we have put temp.next equals head. So this is pointing temp.next to the head of the previous object, creating a chain. Now in a linked list, the head always points to the beginning of the list. So this means that we would have to move the head. To move the head, we simply use one line, which is head equals temp. So now head reference points to the memory location of temp. There you go. Let's add another node to it. Like before, car temp equals new car. So notice instead of creating a third reference for my third node containing 3, I am reusing the temp reference that we previously created. So car temp equals new car, temp.val equals 3, temp.next equals head. Using the same logic, we store 3 in temp, and now we're pointing temp.next to the head. Now, as I've said earlier, in a linked list, head always points to the first node. This means that we would have to move the head. Like before, head equals temp is going to move the head to the temp. Again, adding another node in there. Same idea, and reusing temp. So car temp equals new car, temp.val equals 4, temp.next equals head. And finally, moving the head to the first position of the list. If you notice, head.next is the node containing 3, .next is the node containing value 2, .next is the node containing value 1, and this last node .next is null. Alright, let's make a small modification to our code. If you look on the left side, the code for the class, I have defined another constructor. This time it's an overloaded constructor with 2 parameters, integer x, which is initializing the value in the object, and car nxt, which is initializing the value next within this object. I'm going to exploit this constructor to write simpler and shorter code. So all the code that we've seen in the previous slide could be replaced by these 4 lines of code in front of you. Let's look at this code. So we're simply saying car head equals new car 1, null. That's going to initiate the overloaded constructor, creating a new memory location, storing 1 as value and null as next. Now I have a loop for integer n equals 2, n is less than 4, n plus plus. This loop would run for the values of n equals 2, n equals 3, and n equals 4. You should stop at when n becomes 5. In the loop body, we're creating a new object with temp. So we say car temp equals new car, n comma head. N would be storing the value of current n. So currently n is 2. And head is pointing to the first node created before the loop started. So here we're simply saying temp.next would be equal to head, and realign the head, so we say head equals temp. The loop is going to run 4 times, and when the loop terminates, you would have a link structure similar to the one on the right side of the screen. Here's a small exercise for you. Extend or modify this code. So instead of having a list of size 4, you create a list of size 10, storing values starting from 1 to 10. I'm going to pause this for a few seconds, and then I can come back to it. All right, here's a solution. So we define a variable integer size equals 10. The rest of the code is similar. The only difference here is the loop now is going to run until size. Whenever the value size is reached, we're going to stop the loop. So this should create an object. You should create a list of size 10, where head is pointing to the last node containing 10. Head.next would be pointing to an object containing value 9. That object would be pointing to an object containing value 8, and so on. This is the end of this lecture. Thank you very much.